But let's keep going. Next challenging problem I'm interested in is solar refrigeration. Refrigeration is a huge challenge, especially in the summer when we all run ACs. That's going to be one problem. Or if you want to keep medicines cold when there's a disaster, so in typical refrigeration, what happens is, I'm not going to run the video in the interest of time, but typically what happens is the heat engine runs in, so you remember you had a hot region and a cold region, and we use the hot region to heat something up, which becomes a vapor, which runs the turbine and then goes to the cold region, condenses, becomes a liquid, and goes back. In a refrigerator, it happens in the reverse. So essentially, when something evaporates, it takes heat out of the refrigerator. When we run, we perspire, and the sweat evaporates, you cool down. That's why you perspire, right? The exact same thing happens in a refrigerator. The working fluid essentially evaporates, takes the heat out of the refrigerator, becomes a gas, and then it runs through a compressor, which compresses it down to a liquid, and that liquid then is passed through a very small nozzle, which expands really fast and becomes a gas again. So there's some detail here which I'm kind of not important for us, I think, anyway. But the question, and that is run with a compressor. And remember, the compressor has to run in a constant velocity, as we talked about before. And it's very expensive to run electricity, right? We all know this. We have to pay huge electricity bills when we run the AC. So is it possible to use sunlight to do this? That's it. Can we make ice? By the way, the answer to this is yes. And this was discovered by the ancient Iranians, the Persians. They had a solution, I think, like 2,000 years ago or something. It's called a zir pot, or I forget the exact name, but if you Google it, you'll find it. There's some really interesting prehistoric things that they made in the desert. They could make ice. We'll come back to that later. So one obvious way to do this is, again, with photovoltaics. This is the naive approach, just like in the MIT case. You can use a PV, have it do the work. By the way, this is a nice way to think about the work. The work done by the solar panel is simply the current generated, the intensity of the light multiplied by the area of the solar panel. That's the input from the sun, right? The intensity is in watts per meter squared. Okay, watts, joules per second per meter squared, multiplied by the area is meter squared, so I get watts. It's the power in. And it's going to run current through here, okay, so as shown, and runs a DC motor. It does the compressor, and it does the heat engine and cools something. Okay, that's one way to do it. It has the same problems as the MIT case where the clouds and all that, you have to deal with the controls. It can be done, but something to deal with. So you have to deal with the battery, variable capacity, and all that stuff. Efficiencies are not great, about 30%. It can be expensive, depends. One of the challenges here, the compressors, is the mechanical thing typically, not great, and you have this moving liquid, right? Not a great thing. There is another option, it's an interesting option that you should be aware of, something called thermoelectric cooling, which is basically an electronic device. It's a solid state device. Essentially, it's a PN junction of a particular type of material, which conducts heat in the same direction as current. Okay, there are a few special materials which do this. For example, bismuth telluride. So what you do simply is you take a PN junction, which is one side you have holes, another side you have more electrons. So this is P-type bismuth telluride. That's N-type bismuth telluride. So there's more electrons here, more holes here. So those who have taken 3,200, 3,300, I can't remember. There is a voltage difference between the two sides when you put them together. So voltage difference which prevents the charge carriers from going through, okay? And when you apply a opposite voltage, in other words, you force the carriers to go through, the carriers go through, it produces a current. Okay, that's like a diode, basically, right? All of you know what a diode is. You run it in the reverse bias. So you run this current. But what's interesting is that as the electrons, so for example, the holes travel this way and the electrons travel this way, both these particles, in the case of holes, they're quasi-particles, but they carry the heat as well, not just the current. So this, you force the current to flow that way, it also flows the heat. So it absorbs the heat from this side and goes over here and rejects the heat on this side. And that's called the thermoelectric effect or the Seebeck effect and so on. Okay? This is great because there are no moving parts. It's solid, completely solid state. And can be very small, very portable, relatively low efficiency, and incredibly expensive. But this is one of the only things we can use in space. So the Mars rover has to use it. There's nothing else we can do. Why do we need to use it on Mars? Because the daytime temperatures are like 300 degrees, right? You don't want the electronics to fry, so you gotta do some cooling. Yeah. Same thing in most parts of space, right? And you can't cool it with you can't run a turbine. Right? What if it fails? This is the only thing you can do. It's expensive. That's what you live at. You can do a nuclear reactor as well, which is what you do for deep space missions. But anyway, that's a different situation. You can also think about a solar thermal refrigeration, which uses the heat directly to run a heat engine. So again, I won't go into the details here, not terribly important, but essentially, you can imagine it has some sort of fluidic channel which heats up the liquid, and the hot liquid, in the case water, it goes this way, cold water comes in, and you can use the difference in the temperature exactly as before to do some work, in this case, to run a compressor or whatever it is, right? Of course, this is very common, not so common in the US, but I think if you go to Germany or actually in China, the panels on the roofs to create hot water is incredibly common. It's a very simple system like this. And they can use evacuator tubes or anything like that. But yeah, essentially heat is an input to the engine for cooling. Of course, challenging. One of the key challenges here is that in order to collect enough heat, you need to have a large collector area. However, large collector area also means you're going to lose a lot more heat. So you really need to engineer these systems pretty carefully, I would say. The other thing is, the other interesting thing, we'll come back to this again. I just want to briefly mention that the heat engines always work very well when the hot and the cold regions are highly separated. This is really what we want. In fact, we'll come back to this in almost every lecture, every other lecture or so, up to the last. Because this is the Carnot efficiency. And this is an important equation. We'll come back to this. Carnot efficiency is simply 1 minus temperature of the cold part divided by the temperature of the hot part. Okay, we'll come back to this. You don't need to memorize any of this, but so if I increase that or decrease that, I get closer to 1. And this is dictated by thermodynamics. As many of you probably know. Yes, we have a few minutes of introductions. I went really fast, so I'll stop. I kind of breezed through a lot of things, so I'll stop here and see if there are any questions. Also on Zoom. Sorry about that. Yeah, I thought I didn't have enough time. Good. Of course, there are many other examples I can talk about as well. Let me see what examples I can say. There was an example of a team that did daylighting, which was very cool because what they did, they designed a system with fiber optics and things like that to bring sunlight in. And they had a model house, like a toy house, like my daughter has one, I know. And then they actually had a little collector, and they had fibers inside, and they lighted with a flashlight like a sun and showed that it works. That's a really interesting example of a demo, I thought. So there are a lot of challenges there. How do you collect the sunlight? How do you bring it in without losses? There's a lot of very interesting problems. How can you make it modular? Can you retroactively fit it into an existing home, or can it only go onto new construction? All of these are not necessarily only business questions, they're technical questions. That's the way I want you to think. Another good example, this is a very, very smart student. He was a PhD student in my lab. Before he became a PhD student, he took this class. They made essentially a smart garbage can. So all it does is we wanted to talk, we talk about optics for recycling. All it does is that you put in a bottle, like the one you have there, the camera reads the number, at the bottom there's a number, and there is a little motor that determines which compartment in the garbage can it should go into. Oh, this is, anyway, it kind of looked like that, a cylinder, and there were lots of containers. And they designed it, and there's a place to put it in, and there's a camera and all that. But they only did a wire grid, and they did a simulation in MATLAB. Actually, they did a printed circuit board, a little model with an LED to indicate which chamber it will go into, so like a model. So it's not exactly. So there's another example. Let me think of any more. There was a team, an online team actually, which was pretty interesting. They ended up meeting in person and building a water desalination system in someone's garage. And it was quite cool because they used a concentrator, and they didn't, of course, come to the class, but they took a very nice video, and we saw some drops of water coming through, and I think they drank it. So it was pretty cool, yeah. Lots of examples like that over the years. And I said yesterday, one of the teams a couple of years ago actually did the app. In fact, last year we had a team which did a machine learning project, which was actually very cool now that I think about it. They use the data, there's publicly available data of the sunlight, obviously, solar installation, but also weather and I forget what other data. There was a bunch of open source data, and they used it to train a machine learning algorithm that was able to predict how much energy could be generated for a particular solar installation. And it was like a predictive network, and they actually tested it, and they had a whole business plan around it, which was quite cool. Yeah, there's a wide variety. There was a team that worked on vertical indoor farming, which is another interesting idea because, of course, farming requires, interestingly, precision farming requires lighting, and we'll talk about it later. And lighting is an optics problem. The color, how do you control how much light, where do you install it, what's the timing, how do you optimize the power, time, all that kind of good stuff. And they did all that stuff too. And I believe they talked to a bunch of farms, and they had a lot of data, which is the other thing. The second half of the class, you will be talking to, hopefully, customers to get feedback. Okay, let's go quickly through the class. If anyone, we only have 5 minutes. So if you don't mind, just say your name. And I'm sorry if I put you on this. If you're super shy, I guess you can skip. But just say who you are and anything else you're interested in the class. You don't mind starting at the very, and you can go in a serpentine fashion. You don't have to stand up, yeah.
Okay, yeah, my name's Ian. I was really interested in this class just because I thought that the description was really cool.
Okay. If you have an interesting project thing or something you're excited about, let me know. Yes. Dylan. Aiden. Okay.
I'm kind of interested in the water desalination.
Make sure you put it in the poll.
Yeah.
Okay. Great, yeah. That's good. Have you had any experience?
No.
Good, good. It's a good way to learn. Please. Okay, okay. Oh, hopefully you'll get something out of it. I'm sorry you're forced to take it. By the way, if you're not from ECE, also let me know. Any of you who I just missed? All from ECE. Okay, good.
Emmett,
yes.
I've taken your class before, and I really like more hands-on approach.
Yeah.
Not so much like paperwork involved with that, but
yeah, this is a bit more paperwork.
Yeah, but I don't want that either.
Okay.
Because again, it's still kind of like
yeah.
works well with like what we're actually experimenting with.
Yeah, I hope so. Yeah, good. That's a fun class too, so you guys can ask. Unfortunately, that I have to restrict. It can't be this big. It has to be much smaller, but that's a really fun class. Yes?
I'm Jason. I'm interested in more space.
Excellent. So there is an article. I will put it on Slack later today. You should read it. Very interesting blog post about a nuclear reactor design for space travel. And it's really based on a heat engine. So you will appreciate it. I should remember to post it. I just read it yesterday. Okay, great. What's your research? You must be a grad student.
Yeah, same.
What are you guys research? What's your research?
Radiation.
Okay, then I should definitely send you that post. Yeah, it's a NASA mission essentially. Yeah, please. Okay, good. Okay, so one year there was a group that worked on a sterilization system using light. Might be interesting. So how to make it simpler, cheaper, so anyway, yeah, if I forget, maybe send me a note. Or if you fill out the form. Yes, go ahead.
My name's Sam. Kind of similarly to the space radiation stuff, I work part-time for Los Alamos National Lab. I've got an instrument on the ISS right now, and I'm dealing almost day to day with problems with heat and radiation effects and stuff like that.
Yeah.
But this specifically, I think about energy and
right. Yeah. So
I'm excited to take this course.
Great. Yeah. So it's good that we come in with some experience. We will talk about passive cooling later, which is an interesting aspect of this whole business of. So I didn't mention this. So we use ECE for cooling our home. There is a way to actually do this completely passively. There's a group out of UCLA and Stanford who's pioneered this called passive cooling, essentially creating nanostructures, so structured materials which will emit very, very efficiently in the wavelength band that is transparent to that the atmosphere is transparent to. So the space is actually deep space. If you look up at the sky, that is very, very cold, right? Your building, your house is hot. So why not treat that as a heat engine? In fact, that's going to be the last lecture. So I'm actually very excited about this area. It's not my research, but it's very, very interesting. So I think some of this might apply to this radiative cooling business. So it's a radiative cooling, but radiative cooling that is engineered spectrally. So you allow the emissivity to be very high in the window that can penetrate the atmosphere. We'll come to that later. Sorry, go ahead.
My name is Daniel. I work for the Air Force, and I'm actually used to the photovoltaics.
Great, yeah. How can we keep a drone in the sky forever? Right? Can we power it with the laser? It's a big problem, yeah. My lab does a lot of work with it. Yeah.
I'm Connor. I'm just generally interested in like renewable energy and solar stuff.
Yeah.
This is
great.
The first class that I've seen so far that has solar in the class description. So.
Okay. Hopefully you'll do something. Yeah, I hope you'll learn a lot. Yeah. Yeah, by the way, I should make a quick comment. As Amit mentioned, I'm not a big fan of doing a lot of papers work either. Although you have to do this in this class, I really would like you guys to do some hands-on stuff if possible. It's hard to do it, I understand, but just quick comment. Yeah, please.
Well, hello, my name is Yizan. I'm really interested in like the optics side of solar panels.
Yes.
And how to actually have the sunlight reach the solar panel.
Okay. Yeah, we'll talk a lot about this. Yes.
I'm Caleb. I got the privilege of taking a class on optics before, and they're like, by the way, there's this thing called geometric optics. If we are going to talk about it, you'll have to go to graduate school to take a class. I made it to graduate school. I'm taking that class.
Okay, great.
Life dreams are being fulfilled.
Okay, very good. But my advice for you is we will only touch, it's like a tip of the iceberg. If you really want to learn these things, you got to do it yourself, like as part of a research project or something like that. Yeah. PhD, yes. Yeah.
Gosh.
Excellent, yeah.
Push forward.
Yeah. It doesn't, you don't need to be a grad student. You can still work and do a PhD. Yeah. There are many options.
The space radiation part as well.
Okay, great.
Is kind of related to it.
Yes, you're a Hyung student.
Yeah.
Yes, okay. So you are looking at planetary probes, is that the idea? The planetary probes to send to other planets?
Yes.
Okay, got it. Okay, very good.
Hi,
my name is Photon Lee, and main interesting part in this class it might be photovoltaic or photo radiation things here, because my research area is about some usual webpack and material.
Okay, very good.
About power devices and
Okay.
UV detectors.
Okay, excellent. Yeah, we will talk a little bit about light trapping and light extraction from LEDs and solar cells. Yeah, so a little bit on the light management side. There's a lot of work, obviously, on what to do to the light so it can be absorbed more efficiently, or if you're an LED, how to extract light out more efficiently. Obvious problem, right? Your phone, your battery dies. If you can make it more efficient, obviously it'll last longer. So big industry around it. Please.
I was telling, I'm interested in already just off-grid kinds of
Yeah.
systems, so it boils down to energy.
Yeah, that's a huge challenge. Yeah, but if you, there is a really interesting company here. I think in Provo, Zero Power. I think they're called. Yeah, I'll post it once I remember. Yeah, there's a company in Utah which is doing some really great things in the completely off the grid solar and battery and things like that.
So my name is Mohammed, and I'm more interested in the entrepreneurial side of engineering. So this was the first that I saw about this. Right.
Yeah, great. Yeah, we'll do a lot of that. Yeah, it'll be quite. By the way, this class I should also mention is. Sorry, I'm going a little longer, but I'm almost done. It is a little bit self-driven, right? As you have to kind of put in the work. I will help you, but I'm not going to kind of spoon feed you. You guys, you're all very mature now, so yeah.
I'm Lauren. I'm a student engineer at Rocky Mountain Power right
Oh,
now.
Great.
And I took this class because I'm interested in the business side.
Okay. Yep.
And I wanted more like a realistic engineering class,
Yep.
of what it's going to be like in the real world,
Yeah,
rather than just sitting and deriving stuff.
Yeah. Good. I hope it's useful. Yeah, I think that this is where the teams are important. So you really need to kind of work together to build something important. Yeah. Good. Well, I'm glad you're here. By the way, when you said document, one of the things that came to my mind is I never talked about it, but wildfire is a really important problem, and there are lots of problems to solve there, like wildfire detection. You know, are there resources we can do for fire mitigation management, things like that? So I'm actually very interested in that. So maybe there's a team which might be interested in this. Yes, please go ahead.
I'm Amy. I took this class because I'm not too familiar with optics.
Yeah. Yeah. Excellent. Yeah, this will be like really touching the surface of optics. Yeah, optics, century-old field, but very exciting field. So glad you're here.
I'm Dylan. I took this class because I wanted to branch out a little bit and just explore some more areas.
What's your home area? What you feel most comfortable with?
Mostly power automation and controls.
Okay. Yeah. So it's not that far. Okay. Great. Yeah. Fantastic. Excellent. Well, thank you, everyone. So, and thanks for staying a little longer. So next week is important. It's going to be geometrical optics, your first lecture, and there will be some math. So don't be scared. Yeah. There will be homework. So make sure you start practicing it. I don't mind if you collaborate on the homework. In fact, I would encourage it. Because sometimes talking to your peers helps you kind of understand the concepts better. And if you have any questions, please message me on Slack, okay? Even if I'm not here, I will message you back. See you guys. Thanks. Go ahead.
Just a